Hi everyone, good evening to all of you. Thanks a lot everybody for joining in for the today's webinar on practical demonstration of cell impedance analysis. So we will wait for some more time, and then we have good about 100 people who are willing to join today for the session. So we will wait for some more time for everybody to join in. So until then, I think, Vinayak, if you are able to allow for everybody to unmute themselves, we can have a quick interaction with all the participants to get to know what interests them to be a part of today's webinar.
Yes, everybody can unmute and
you have enabled option, Vinayak?
yes, have enabled.
All right. So, hey everyone, just because we're supposed to start at 5:30, I understand that not everybody joins on time. So just to make sure everyone skip things, we would like to know, because we have about a good number of participants today, would be glad to understand what interests you to take part in today's webinar. What is your learning expectations from the today's webinar? With that note, I think we can spend a couple of minutes, let's say about 5:37, and then we should be good to start our anybody can unmute yourself and then just set the stage right there. Start. Any of you would like to have inputs from your side for a quick chat and to let us know what interests you to be a part of this webinar? I hope you have an option done. Or you can also send a message.
Yeah. Hi team. Myself, I am Vishnu Karthik. Actually, I have more than 5+ years of experience in this battery pack design development. Particularly, I have worked as a electromechanical design. So from this meeting, which I want to come to know about this different kind of welding technology, because of that, how much resistance impact is happening. So these are the things which I'm willing to learn, because while we are doing the theoretical calculation to calculate the overall module level resistance, power loss calculation, by the time I'm not able to predict the if I'm going into the spot welding, what would be the resistance, like how much percentage I have to consider, or else if I'm going in with to laser welding, what would be the max to max resistance. So overall battery pack level resistance calculation depend on that, how much power loss will come, how we can efficiently improve our battery pack efficiency. So these are the topic which I'm looking forward to learn in this meeting.
Fantastic. So
thank you
for Vishnu to start the open points. As far as I understand today, we would look more from the cell perspective. In the upcoming session, so we also have pack level, ACIR testing. But right now, for today's session, we are performing EAS at a cell level. So we will speak more about that today, okay, and then go more in depth on the side of the cell. Maybe in the next session, next upcoming webinar, I try to bring in the pack level studies, and then we're going to check how that would contribute to the picture of it. Yeah. Great. So and then we do see some more participants who have come up to your question, your inputs, what you're interested in know. I'm a research engineer, so mostly we deal with applications related to cells, so I need to understand EAS to know the performance of the cell. That's good to know, Mr. Isam showed. Then we also have Marcella Prasad, so working with hardware engineer, test troubleshooting of PCB components. Interesting. I'm not sure how well it relates to the PCB part of it, but yeah, I think mostly on the battery side, we're going to talk about today to our good understanding. Awesome. So I think we have another 2 minutes to kickstart our webinar. So if anybody would like to let us know what is your expectations from the webinar today, we'd be glad to understand the context from everybody. You can just drop the messages as well. We would be good to know what sets the stage for and what backgrounds the participants are from for this webinar. Cool. So, and it's pretty good to see that Friday evening, we have people about 55, and that's the biggest number, I think, till now. And we have even more number of people joining. Looks like everybody wants to learn.
Very interesting.
That's awesome. So I think this is the first time as well, we are able to come on a video and show our lab facility, and until now it's all through presentations and
theoretical.
Absolutely. But today, you get to see the hardware that we use, and from there you get data and stuff like that. Cool. So I think we should be good to start. People whoever would like to join today would have joined by now. I think we have one more gentleman to read his opinion. So I'm going to get an industrial research problems perspectives. Okay, awesome. So great. So thanks a lot everybody for joining me for today's session. Good evening to everyone, by the way. So welcome to the webinar on practical demonstration of cell impedance analyzer. So as we briefly call it as EAS, electro impedance spectroscopy. As a part of today's session, so I am Suraj. I'm the founder and CEO of Decibels Lab. I will be the co-host of today's session, and we have Abhinav. Over to you, Abhinav.
Hi, good evening, everyone. I am Abhinav. I'm a simulation engineer at Decibels Lab. So today I'll be demonstrating the functionality and the working of this cell impedance analyzer. So basically, we take the complete overview of what is EIS, why do we conduct it, what is the purpose of doing it, what outcomes do we get, and some graphical work.
Absolutely. So until now you haven't seen Abhinav, but today you're able to see in person, so I could bring him up. Until now it's just backstage, but now just to showcase everything. So we have Abhinav on the screen as well with us today. So with that as a context, let me just put across a quick brief idea of Decibels Lab. So Decibels Lab is a company based in Bangalore. Primarily, we support a lot of learning activities in the areas of electric vehicle technology. And that battery is a very core area for us, battery management systems and the powertrain. So we work extensively in these 3 areas till today in that. So I think we are the education institution, the only education institution I think have a lab facility, the state-of-art lab facility that is equivalent to any foreign universities, to create a full-fledged practical hands-on learning to the participants who come and learn. I think we are equivalent to any part IISc or IITs around the country as well, which creates and enables anybody to come and do a real-time learning and research here as part of the learning activities. So with that introduction, the lab has a lot of battery characterization activities. So we are sitting in the part of our battery test facility. So we have on the back side of this image, the video, we have a lot of lab for cell characterizations. So maybe just if I can just quickly show you through the other video. So show you the process. So we have a fantastic lab that also enables the opportunity for many learners to pick the great scope of learning through this lab. And then on the other side, which we are representing to you today, we have all the pack level testing and also the EIS measurement activities as well. So glad to have you here today. And about the topic of today's webinar, so that's on practical demonstration of cell impedance analyzer. With that one, I will hand over the session to Abhinav to just set the context of the session and then also flow of the chapters, and then let us start with the topic itself.
Yeah. Yes. Thank you so much, sir. So warm welcome everyone. Welcome to this webinar. So I think as sir has mentioned that our topic today will be focused on impedance measurement of a lithium-ion cell. So the objective of performing this, basically the electrochemical impedance spectroscopy or EIS, basically it is to understand the in-depth performance, the in-depth impedance values of the cell, So one by one, we'll try to understand what are the different components of impedance, what do we mean by impedance, basically how we define the components of EIS, and then further on, we have a short quick comparison between the DC method of testing impedance versus the AC method of testing. So basically, EIS, as mentioned earlier, is called as electrochemical impedance spectroscopy. It's a very detailed test that falls under the characteristics of AC, basically alternating current characteristics. So it's a totally different branch compared to DC characteristics. So why do we perform EIS and why it is sometimes much more preferred than DC characteristics? The reason is because in EIS, you're able to split up each and every component within the cell, the impedance of the anode, the cathode, the electrolyte, the current collectors, the active materials. So each and every one of these components and their contributing elements is very clearly visible when you do EIS. So which is something you cannot see in DC characteristics. So what do we do generally in a DC approach? What we do is we fix a cell into one of the testing devices. I believe sir has shown some of the devices. So in one of them, you fix it in a jig and then apply a DC pulse, a current pulse. Then you get a DC voltage as an output. And then from there, you just use V is equal to IR and find out the resistance. But that is very simple. You don't get to know what is the degradation mechanisms. You don't get to know the in-depth contributing elements and components within the cell. What is the anode, what is the cathode, what is the condition of the cell? All those things are not clearly visible. Which is why we go one step ahead into something non-standard that is called as AC. So ACIR, alternating current internal resistance, and also a much more elaborate version of that is the EIS, electrochemical impedance spectroscopy, which is what we're here to explore today. This is what the device over here does. So this here, yeah. Yeah. So yeah, I believe if my screen is visible to everyone. So here, basically we have what is called as an impedance plot, or also called as a Nyquist plot. So this is much later. I will be explaining this in a bit of more detail as we come closer to the end of the session. So the idea is to understand what are the different contributing elements to impedance. That's basically what is the outcome of EIS. So what you're observing here is the total impedance of the cell represented as a combination of real impedance and imaginary impedance. That's basically what the Nyquist plot shows here. So as we proceed further on, we'll try to understand how do we derive this Nyquist plot, what are the contributing elements. Some elements of them, the major elements of EIS, is diffusion. So ionic diffusion takes place within the cell. So to what effect it takes place and to what extent you can see it, all that is visible in this graph, followed by the charge transfer, the chemical resistance, followed by capacitance, inductance, and solution resistance. So all these are different components, different active material components and chemical components present within the cell, and how to what extent they contribute to the cell's functionality. That is where we measure the impedance. So that is what we see here in this output. This is the output graph. It's called as a Nyquist plot. Again, I say the same. So this is what we will be measuring both graphically and numerically in this device. So that is the idea.
If I do understand that, we're gonna conduct a test and then we get a data from the machine.
Yeah.
So that machine data would come plot Nyquist graph, Nyquist plot graph.
Yes.
Right? So that's the graph, the way of the graph would come if you conduct at a very specific frequency range.
Yes.
And right.
Yes, that's correct.
And also those graphs are very specific to specific SOCs.
Yeah.
Of like the parameters of the cell are varying with respect to state of charge.
Yeah.
And I think they're also varying with respect to temperature as well.
Yes.
Right. And I think they also going to change with respect to the age of the cell as well.
Yes.
Right? And so if we get the data of the cell, so what we see on the screen right now, as you said, there are a lot of components such as charge transfer resistance, diffusion resistance, maybe the other type of resistance that comes into overall pixelization part of it. So we try to get this graph.
Yeah.
Then from this graph, we're going to pick up certain portions of the graph to identify
Yes.
what components of those parameters
Yes.
would be falling in which part of the graph,
Yes.
right? If that's what we're trying to look through the graph and try to get.
Yes.
data.
Absolutely. Yes.
Okay, great. So let us go now, and I think we can stop the screen sharing, and then we can go now to deep dive for the visualization of the machine itself.
Yes. So I think you can just put the video to show the
Yeah.
screen.
So let's put this video across.
So in the meantime, I think I'll quickly just explain what this device does. So this is a cell impedance analyzer. This is basically a device that can do it for a cell. We do have one that does it for a battery pack as well. That is going to be demonstrated later on, I believe. So in this device, you can see the arrangement of the cell, which is connected using these electrodes. So this is a positive probe and a negative probe. So we just connected like this. These are just the alligator clips, and we just put them like this. So with this, it will be connected to this device through the potential junction. So this is the potential junction. So the device then measures the voltage and the impedance both through this wire. Now, in this screen, you can just check all the settings as well. So the same thing is visible using the software. So now I'll open up a mode called as the analyzer mode. So in this analyzer mode, you're able to conduct this EIS, electrochemical impedance spectroscopy. So here I will just open up the settings. Okay, so basically in order to measure the EIS, or basically to measure the impedance of the cell, we conduct this test between a frequency range. So this is necessary because, as I mentioned earlier, there is something called as a contributing elements, and each element will contribute to impedance at different frequencies, right? So we have a small frequency range or a very low frequency range, then we have a mid frequency range, and then we have a high frequency range, and then finally we have an ultra high frequency range. So that is how we are able to observe all these components. Basically, that is how you get the Nyquist combination of all of these frequencies together.
Right.
So in a short time, I will explain to you what that means. You're able to see the frequency values over here, start, stop in hertz. So I'll come to that. So before that, I'll explain what are the parameters that we'll be able to observe. So if we just click this drop-down option, I think we can see all of the impedance values over there. So starting off with Z, which is just a generic value, just impedance. It doesn't talk about what type of impedance. And then we have so many other values as well. You can see pH, that is the phase angle. And then you have RS, which is the series resistance. Then we have RP, which is the parallel resistance. Series capacitance likewise, and parallel capacitance. And then many other elements you have. You can see this G, which is conductivity and other things, inductance, and many other parts of the impedance. So overall, this device gives you a complete split up, or you can say spectrum. That's what we call it, spectrum of the impedance by performing this AC test, the EIS test, right? So generally, what do we do when we conduct an EIS test? We start with parameter as RS. So RS, basically, that is your series resistance, and parameter 2 is your imaginary impedance, which is X. Okay, so this is basically what is the contributing factors for your Nyquist plot. The Nyquist plot is formed between these two elements. So now, the other parameter that we vary is the starting and stopping frequency. So at what point or at what frequency does the testing start? So as I mentioned again, that the testing is usually performed between a frequency. So this frequency range, you can start it at very low frequencies, something like 1 millihertz. This device is capable of that. This device can go as low as 1 millihertz, which is not so easily available in many such devices. And it can go to a maximum frequency of 200 kilohertz. So that is the complete sweep range or sweep capabilities of this device. So for ease of understanding and for ease of representation, we will not be going for the entire range because that will take 1 day or 2 days of testing. Right. So what we will do here is just for representation's sake, I will put here as 1 hertz as the starting frequency and the ending frequency is 5 kilohertz, or you can see a 5,000 hertz. So that's basically what you're seeing here. 1 hertz, we start at 1 hertz and then we stop at 5 kilohertz, right? So with an interval of 201 points, it will measure all the impedance values between the start and stop frequency. So that's the settings that we see here. We just have to click OK. And basically now the instructions is being passed on to the device. Right. So now we're ready to measure this. So I'll click the button over here. You can just see trigger. So I'll just press that. And you can see right here on the device screen as well, the measurements will start to show up. Yeah. So you can see, so as we had performed the settings, RS and X. So these are the two contributing elements for your Nyquist plot. So you can see that it starts at 1 Hertz and the frequency goes on increasing. So your frequency of AC current, the current that is being input to the cell from these clips. So they go on increasing, and you can see your impedance values also changing slowly. So this is one of the simplest ways in which you can perform an ERS test.
Right.
So in a matter of few seconds, I suppose you can get the results, because we know that time and frequency are inversely proportional, T is equal to 1 by F. So basically, if you go on increasing the frequency, your time also goes on decreasing. That's how you're able to observe the results here.
So, like I think now we spoke about 1 millihertz and also 5 kilohertz. So is that something which is very specific to a cell, because that's what the frequency we need in the machine?
Right. So it is the frequency range by itself is not something that is specific to the cell.
Right.
It is the frequency analysis points that is specific to the cell.
Right.
So each point and the range or the region within which you analyze, that is specific to the cell.
Right.
So I think in that terms, that is where you can segregate your Nyquist plots and try to understand it.
I think we can understand more by looking at the data that the graph that comes in.
Yes. So I believe you can see the 5 kilohertz data that has come now. You can see how different RS is compared to at the lower frequencies. So I'll just go over to the graph points. So this is just the numeric values, what you're seeing over here. So I'll just go over to the graphical points. So now this you can see, this is called as a Bode plot. So usually Bode plots are not so directly easy to interpret. Sometimes we need to go for some logarithmic things like that. So we will not be seeing this over here. Instead, we will go for the pole plot, or also known as the Nyquist plot. Right. So when I was explaining Nyquist plot, I believe I started off at a slightly higher point. But now you can just break it down into something little bit simpler. So here you can see that there is a semicircle or a semi-arc formed. It starts over here at the right-hand side. This is the low frequency region, which we started at 1 Hertz. And then from there, as the frequency goes on increasing, it completes one full arc, or you can say one full semi-arc over here. And then it crosses over from positive to negative and then goes off into the imaginary region.
Right.
So this portion is the high frequency or the ultra high frequency region.
Right. So when I say the 5 kilohertz point of it, the data coming from the 5 kilohertz is going somewhere, here in this section of it.
Yes.
And then whatever that's the 1 hertz that we have said would be falling somewhere here
on the right hand side.
on the right hand side.
Yeah, on the right. So again, just to simplify, the frequency is lowest on the right hand side and it goes on increasing towards the left side.
Right.
That is how you interpret a Nyquist plot.
Right.
So it is from this plot basically where we can go into post-processing and other analysis methods.
Right.
So
before we go there, can we go back to our software and just try to look through, how do we, if we want to get a diffusion resistance, right?
Right.
So maybe we can go back to the set and So I think for somebody it is I think as it is a video as a part of it, the screen share is not there. You can we have pinned the video. Okay, there is nothing shared in the screen as a screen sharing. It's visible to you on a camera. Go to the specific person's video. I think I've spotlighted the video. If you see that, I think it should be visible for you. There is nothing shared on the screen right now. Yeah. Vinayak, is it visible that the specific camera that is turned on? Is that visible?
Yes, it's visible.
Oh, all right. So I think coming back, Abhinav, so as a part of it, I think somewhere here on the screen, so we said 1 hertz as a frequency, right?
Yes.
I think that is when we said 1 hertz, I think we are only limiting ourselves here as a point of it.
Yes.
I think when we said a lower frequency, maybe like a 0.1 hertz or maybe even lesser than that, we intended to possibly see a bit of a more from a Warburg impedance perspective.
Yes.
Right?
Yes.
That's what I think we can just try to set a value.
You can do that. Yeah. So quickly before I set that value,
Right.
so Basically, the idea of explaining this first and not the Warburg impedance
Right.
immediately is to understand that these are basically just to show what effect you get when you choose a frequency range like this.
Right.
So you are not able to observe one of the major components within the cell, which is called as the diffusion component. So that is visible at a much smaller frequency or a much lower frequency. So instead of setting it at 1 hertz, if I set this as 0.1 and then allowing my higher frequency to stay the same, I'm just reducing the start frequency to 0.1 hertz. Right. I'll just click OK, and now the setting is done. Yeah. So now the device is reset, and all I just have to do is click trigger. And it's the same way the numeric values will be visible in the device screen as well. So now what you will see is that your diffusion component will get added onto this Nyquist plot, and you're able to observe this linear sort of trend line happening on the right hand side again. So I believe that's what we had in the screen display as well.
Right. I think that's pretty much on how the machine
Yes.
is used for
Yes.
analysis of data. Right?
Yes.
So let me just go back to our main screen and then request video on that. So all right, gentlemen, I think if you're able to follow up with what we have been able to demonstrate on the setup here, I know it's just a basic step for all of us to realize that how the data comes from the EIS machine. Okay, few important parameters that we're trying to understand is that the frequency with which we set, we get data from that specific curve. So lower the frequency it goes, so the more the time the machine takes to give us the data as a point of it from that. And then in addition to it, so what are the type of the measurements that we want to do?
Yeah.
Maybe an RS and also another parameter comes into the machine from the data index.
So I think I can show
Yes,
the
absolutely.
numeric values as well.
So what happens is that it takes a lot of time to collect data. If you set one millihertz as a frequency, I think it may take more than about
a day.
About a day.
Yeah. To complete the entire range, starting from 1 millihertz, which is very small. So to sample that and to calculate all the impedance values for just one point would take about 2 to 3 hours.
Exactly.
So if you add up everything, it takes more than 24 hours to finish the entire.
Right. So the scope of it, it is not possible to really say, hey, let me just conduct all tests here and give you some insightful data, right? So yeah, certainly that the objective is that to showcase to you that hey, we're gonna have a machine that is for EIS. We're gonna have the parameters that we can set in the machine, and we can collect data. So when you collect data, so I think we can show to the screen share.
Yeah.
Go ahead.
So I'm sharing my screen right now, and here I'm just displaying one of the sample information that we have collected. So by performing EIS, as I mentioned earlier, you can get your your Nyquist plot as the output. So in one of our test samples, we have started the testing at 10 millihertz, which is the lowest frequency. And then we performed it again till 5 kilohertz. So that is the maximum limit that we need to go.
Right.
And you can see here how the RS and X fluctuates or how it varies with increasing frequency. And if you plot it, you get your Nyquist plot right over here. This is what is the expected output. So yes, in this you can see an inverted version of this. The same thing that you would see on the device display. It's just that this is inverted. It's the same graph. So it is from this graph basically that you can analyze each and every component. So as we mentioned earlier, the series, the solution resistance, the inductance, capacitance, and things like that. Right. So I think if I switch back to my presentation, it's there in this. I suppose I can explain it here.
You can see it.
So yes, so it as I talked about lower frequencies, so you can see this straight line. You can see a straight line here. This basically is the line corresponding to the lowest frequency that the device is performing on the cell.
Right.
So this lowest frequency is what gives rise to the Warburg diffusion, basically.
Right.
So your ions undergo diffusion process, which is a very sensitive and very slow, time-consuming process, and that is visible by allowing the cell to be at very long rest and relaxation periods, with allowing very small low frequencies of your AC inputs. So by measuring the impedance, the voltage output from that, you get the impedance, and that is what is corresponding to the Warburg impedance that we see here.
Right.
So that is a straight line. And then immediately followed by that is, I think, the characteristic semicircle that we see over here.
Right.
And this is the portion that corresponds to the next part of the impedance, the second component of the impedance. So this comes in two parts. The first part is what is called as charge transfer, and I will just abbreviate this as CT. So C stands for charge and T stands for transfer.
Right.
So that is a electrochemical phenomenon in which ions are exchanged between the current collector and the membrane, the outer membrane of the anode. So followed by the capacitance. So these two go kind of hand in hand.
Right.
So that is measured in the semicircle that we see over there.
Right.
Then we come to the third component, which is the intersection between the real axis and the imaginary axis.
Right.
This is, I think, the most important part. So this portion is called as this solution resistance, which I will mark here as RS. So not to be confused, RS over here and RS on the x-axis are not the same.
Right.
Basically, RS here stands for solution resistance or electrolyte resistance, basically. Then after this starts the inductive region. So this is known as the high frequency region, and over here we measure the inductance L. So these are the different components that you're able to observe and how the impedance of each of them basically contributes to the overall impedance and the functionality of this. So that is what we gain
Right.
by interpreting this Nyquist plot.
Got it. I think very well explained that, because so we could see that there's the sections of the plot which connects to the frequency that we set and to which the data comes back to us.
Yeah.
And that's where we are able to relate from the data as well.
Yeah.
But can we just use the data directly? But we're going to use some optimization curve fitting tools, right?
Right,
So I
right.
think would you like to just talk about that?
Sure. So shortly, I think we can have a quick view of that. So we don't directly use this graph as it is or the numerics directly as it is. We have to smoothen them out. We have to do some further interpretation from them.
Right.
So we use what is called as curve fitting, in which we can also elaborate that as equivalent curve fitting, equivalent circuit curve fitting. So we use softwares like ZView or BioQuest or things like these, which allow you to fit this Nyquist plot according to your RC circuit requirements. So if you have an RC circuit or an RLC circuit,
Right.
which is depicting the cell behavior,
Got it.
just like how you have RC circuits for DC networks. So you can use the same data coming in from this. We can fit the parameters, the same components that I talked about, and then you can extract the RC values from there and then further simulate it for the aging conditions and things like that.
So what you would say is that the Nyquist plot is a reference for us.
Yeah.
And from there, if you want to create a model
Yes.
of a cell model,
Yes.
a equivalent cell model, so we will use certain tools like maybe a ZV or also our manufacturers giving us tools,
Yeah.
or software, so that we can do a curve fitting. And from there, you can extract the data from the Nyquist plot, and then that data will be used for creating models
Yes.
of a lithium ion cell.
Yes.
So that can also be slightly done through the DC characterization as well. But if we have an EAS characterization, which can be having more parameters.
More
as well,
parameters.
and
Absolutely.
that gives us a more relatable similarity with the real-time behavior of the
Yes.
lithium ion cell.
Yes. Yes. Absolutely.
Right. So I think that's in a summary what we want to discuss
Yes.
as a whole point of it.
Absolutely.
So I think we can close the presentations, and we have some questions from the participants to just slightly go through. All right, so we have questions from Sahil. Can you demonstrate why all these tests are important? Why is the significant, or there any other way to check the battery cell performance? So I think to answer your question, Sahil, so Abhinav will give you the insights, right? So certain parts of the Nyquist graph is giving you certain information. If there is any impact which is significantly formed with that component, let's say contribution of electrolytes, into the internal resistance of a cell, for example, or an impact of charge transfer in the cells. Let's say somebody is developing a cell, a new cell, or you already have a cell which is you have brought from the market. If I take let's say 10 degrees Celsius, how does that component would behave, whether that contribution will be significant, or over a number of years or number of cycles of the cell, how is that proportion of the component in the cell, material inside a cell, would contribute to a significance of increasing the internal resistance of the cell as well. That's what we relate, that's what we're trying to relate with the data that is coming from the machine. So for a good relatable data, you can just check it in the Google that, if I perform an EAS, a number of cycles, let's say this is cycle number 1, cycle number 50, cycle number 100. If you keep on collecting data, you could really see the data that is coming in a Nyquist plot will help you to analyze what is the contribution of certain parameters and the internal resistance has been significantly going higher or lower as a part of the cell. So that's why we perform EAS. That's one part of it. And the other part is we want to build digital twins. That means we want to build a cell models, right? So that's when you perform the data and test and get the data. And from that data, we extract parameters.
Yes.
And then from that parameters, we will build a model. So that is another significance of the EAS machine. And apart from it, if I can just quickly relate to you, let's say if somebody makes a new cell, they make a new electrolyte and they make a new binding material, or they make any new different compositions as a part of it. Now they want to compare against with previous cell that have different binding materials or an electrolyte and things like that. You can perform a test and then collect data and then interpret the values of it. Is there any other way to check the cell performance? See, this is one of the most significant approaches, if I say, which can give you a lot of data.
Yes.
A significant amount of data, if you can get it. Or you can perform a capacity test. From there also you can check the health of the cell. You can perform DCIR. From there also you can collect and then check the information as well. I think that's what I can give you an answer right now. Would you like to add anything additional to that, Abhinav?
So yeah, I believe that what he has covered is correct. So whatever information you want regarding the condition of the cell, the way in which the cell is degrading, that is why we perform EIS basically to understand at what rate in which it is degrading, the changes in the chemical behaviors. And that is what you obtain by performing EIS. So other characteristics can be classified under DC. So there is a separate webinar for that where we cover the DC characteristics.
Right.
So
it's already done in the past.
Yeah. So there are many webinars in the past as well which has covered the DC behavior.
Right. The next is from the Nishan. If anybody have a question, so please feel free to drop your questions in the chat box. Name the software and instruments using. We are using Hayoki IM3590. That is an instrument that we are trying to use today in our lab. And there is also another equipment from called BT4560. There is another other equipment as well, but that is having a lower frequency limitation. But this one has a full-fledged frequency available for you. And apart from it, the software is given by the machine manufacturer itself. That's what we're trying to use today as a part of the lab. What is the frequency and means? Can you tell which frequency you're saying? Okay. Yeah.
So we are basically referring to the testing frequency that we are supplying to the cell through. I believe if you can just take the setup over here. So you can see that there are two electrodes that are coming in from the machine and connecting to the terminals of the cell.
Right.
So there is an AC current signal that is being produced by the device, and AC current signal at a certain frequency and at a certain magnitude.
Right.
So those values are not always visible to us, but that is input to the cell. And that same set of wires, the same set of electrodes measures the voltage output of the cell, which is also in AC. So the same frequency that you get as a response, you get a similar frequency as a output. So from there, you measure the impedance of the cell. That is what we can understand from this.
I think also there's a previous webinar which also has a description of our selection of
Yes. There is a theoretical webinar that we had conducted very recently on this. Please do check it out.
Vinayak can share the link of the previous webinar on the years to all the participants. They may have some doubts to refer the previous webinar as well.
Could you please show a close-up of the physical connection? So I think somebody's requesting this setup once again.
So just a quick possibility is that I need to make this as a spotlight. So if somebody wants to see the one that is visible here for all of you.
Just
Yeah,
pull this out for them. So these are the tabs of the cell, if you can just observe.
yeah.
So this is a prismatic cell. And again, just to show the connections, we just clip them like this.
Mhm.
And we are now good to go for the measurement. So it travels through this wire is basically known as the potential wire. So this is where it goes to the device. This is the junction of the device. And this is where your AC signal comes from.
Right.
Right.
I think they're pretty good.
What is the C rating at which charging discharging happens? Right. So Nishant, we are not referring to any C rates over here. Since this is not a DC test, we don't talk about C rate here at all. But if you're trying to ask what is the magnitude at which the AC current is being supplied, we don't know the value because it is a hidden value. But to give you an idea, it is somewhere between 30 to 50 milliamperes of input to the cell.
So that's the clarification for most of them. Like, if you do a DC calculation, it's different. Okay, you could see that the current is being drawn from the cell. All right, that is a little different than how we do it in EIS as a activity. There are key differences between the DC characterization and AC characterization. We would not draw a current from the cell. We don't discharge the cell as a realistic perspective. If you're connecting at 10% SOC, after conducting a test, it will still
be at
10% SOC. It won't, it's not like you draw a current and then it's dropping voltage, things like that. But it is not that way. Actually, if you're conducting a EIS at 100%, 90%, 80%, and 70%, we will remove the cell and then we will keep it for discharge and the cycle. And then we remove 10% SOC and then we're going to keep it back, in the test engine, in the EIS again. So it is not that at what C rate which we perform using the machine here as a requirement.
Correct.
So I think that's the answer for the question. We have a few more questions that we can take it up.
Can EIS be conducted on a battery pack that is already in use, and what is the importance of EIS skills for battery expert?
Okay, I can take that question. So yeah, because there are companies, if I can name them, ADI, analog devices, they have developed a BMS which has an inbuilt, I think, EIS. Okay, right now I was in a conference. I heard that because given some of the initial prototyping activities. So yeah, you can perform in pack level as well. Lot of active research is going on in that area. A lot of active possibilities being engaged to develop EIS instrument in the BMS. So that whenever you identify rest condition and X temperature, you can just perform EIS and then just collect data and then analyze the data on board, or you can send the cloud and then get the results back from the cloud as well. So yes, you can perform. There are very critical things to consider when you're performing. But yes, there are companies exploring the solution development in that journey as well. So that's the answer for you. So what is this? Answer for you, Mr. Victor. When you perform DCIR, ACR, and EIS, would you like to?
Yeah, sure. DCIR is usually performed when you want to test out the DC performance metrics of the cell. See, the thing is, EIS and ACR is only to perform electrochemical tests. They do not give you the performance metrics in terms of DC response. So DC gives you what? Energy, power. It can give you capacity. It can give you DC resistance.
Right.
So charging your CCCV charging, your constant current discharging, constant power deliverance and energy deliverance. Right. That is visible through your DC. So if you want your DC characteristics to be input into your BMS, that's the primary criteria.
Right.
So into your BMS, we use the DCIR. ACIR is to perform cell sorting, especially in the assembly line when you're going for end-of-line testing.
Right.
So that is where you perform your ACIR. There'll be another demonstration just for that. Then EIS is basically what we just now showed you. This is where we get into the deep end of the conditioning of this, aging and conditioning of this.
Right.
So this is the primary difference between all these three types of tests.
Right. Well answered, I think, that question, pretty much well answered. So can we perform EIS even at a pack level? I think that question is answered, everyone. So what is the basis purpose of choosing the low frequency and high frequency? And how would EIS results vary between cell and pack made from the same cells? Okay, so if you'd like to go ahead with the first question, so I can take the second question.
Yeah, all right. So the basis of choosing your low and high frequency is entirely dependent upon to what extent do you want to explore the cell's impedance contribution, whether you want to observe the diffusion, whether you want to observe the inductance region, what do you specifically want from the cell? That is basically your basis. That is your basis for choosing. So for example, as I mentioned earlier, lower the frequency, more the diffusion is visible. So if you choose a very low frequency, say for example, 1 millihertz or less than 1 millihertz even, so you get to interpret your results as a form of one of the most major contributions, that is from diffusion. So as I mentioned earlier, diffusion is a very sensitive and time-dependent phenomenon. It takes a lot of time to observe how slowly and how effectively the ions can enter into the graphite material or into the cathode material. And for that, it requires very low frequency. So that is the purpose of choosing very low frequency. High frequency gives you an idea on the inductance, that is to say, the magnetic effects of the metals inside the anode and cathode.
Right.
So we know that the anode and cathode consists of metals, copper, aluminum. Yes. So they respond to high frequency in a way a conductor would respond to high frequency in terms of magnetic energy. So that's what is inductance in this term. It's just an analogy. It's not the exact same, but it's just an analogy.
Right.
So that is the purpose of going all the way to high frequency.
So how would the EIS results vary between single cell and a pack made from single cells? I don't have a data today if I can show to you, or we have not performed, let's say, EIS at a pack level today. So once we perform, I think we can publish you some data. But certainly we have a lot of contribution of other elements, which would be your spot welding, laser welding, or materials, bus bars, all the components that will contribute. And certainly as a fundamental, electrical engineering that series and parallel combination of cells would have certain series being added. In the parallel, we would have the division of the resistance is going to happen. That's a broad way, but once you perform a test, we can publish you some data and then I'll get back to that. Great. So I think that's really good to see a lot of interesting questions, and people staying back till like about 6:10 right now, 6:20 right now. So can you perform GITT and PITT for the cell? So is there something that?
Yes. So GITT and PITT are DC experiments purely. So galvanostatic intermittent titration testing and potentiostatic intermittent testing. So basically, there are other names for DCR and HPLC. So that can definitely be performed, but that is not the objective here in this particular device. It is not capable of doing that, which is why we have DC equipments for the very same.
Right.
So how much are, the next question is interesting. How much are the DCIR and EIS-RS values related? They are not at all the same actually. They are completely different. If you measure the DC resistance, it is an entirely different category. And if you measure the EIS AC resistance, it is a different category. Because DC, as I told you, it is only a DC response, but AC is a response of each and every individual component. So that is the difference between the two values.
So I think we have another question. As impedance of the cell changes as per the temperature changes while doing an EIS, will you take temperature factor into account, or also what SOC levels of the cell is performed? Absolutely, I think we brought that answer as well in the middle of it, that one way you have a thermal chamber, we can also call it an environmental chamber. You can keep the cells at an environmental chamber so that it is at about an ambient of 25. And you soak the cell as well enough in time that it achieves that temperature at all components of the cell.
Yeah.
And then you can perform an EIS. So that's why the temperatures and impact would be in accounted as well.
Definitely.
I think another point is that SOC. So I think we're also going to talk about that you can't draw an SOC, you can't draw a charge from the cell and discharge it. So you could use a desensitization machines to, like you keep it here, then you remove the cell, and then you perform DC discharge, and then again you keep the cell back with certain resting period and things like that, and then you perform.
Yeah.
Right?
Correct,
So
correct.
that's how we work.
So to also add to that is the relaxation phase that you need to provide.
Right.
So that we have this uniform measurement of EIs.
Right.
So it's not that we just randomly choose the relaxation time. We need to choose about 2.5 to 3 hours at least of resting, and then we go.
Gotcha. So that there is no fluctuations.
Yes.
It's feedback voltage.
Correct.
Almost the voltage becomes settled.
Yes, absolutely.
Then we have a last question. What is the eligibility to work in BMS if currently my role is linked to product products, not BMS? How I can do it? Okay, very interesting question. See, I mean, there is no straight route if it is the way I can answer that question. I don't know how many years of experience do you have to switch over right now. It's definitely up to the possibilities of the industry. The way I look to other people trying it is just try, you get to know. If you don't try, certainly you'll never know if it is possible. If you're in the early stage of your career, I think you can think about it very easy. But if you're in the, I think, later stage of your career, maybe like having 5, 10 years of experience, it's the efforts you have to put, try. I think we have seen people at 25, 20 years of experience trying to come back and learn the courses and then trying to explore themselves in the new areas. So there is no say that you just do it and you get a job. But yeah, if you're passionate about it, you want to do that, you take a thing and then learn and see if it works for you. That's my answer. I think awesome. That's pretty much guys we want to cover as a part of today's session. It's a very quick introduction. More than the learning, I feel like it brings the insight of practicals, what we do, how we do it, and then what relates to that. Where the data comes from, if somebody's sitting there and just watching a presentation of a Nyquist plot, you'll never know where the data comes from, right? How do you set this parameters in the software? And the intention of this webinar as an interactive session is to just get there and understand, hey, see our hardware, this is how it is all set up, this is how the software is, this is how we perform a test, and data comes and parameter you set, and what is that related with the Nyquist plot that you get from the ES?
Yes.
So we pretty much answered all your questions that I put across. If there is no question, that's pretty much Vinayak for the part of the session. If you'd like to wind up and then share the certificate for participation, yeah, over to you, Vinayak.
Thank you.
So I think with Abhinav. So I think that's all from my side and Abhinav's side for today's participation. It was really good to interact and just open up the portfolio to know each other on this areas of it. Thanks a lot, Abhinav, for interacting and spending your time out for the schedule to really host a session on this. Thanks very much, everyone, for participating. It was great interacting with all of you. We look forward to be in a constant learning with all of you guys in the future as well. Vinayak, over to you for the rest of the session. Thank you very much, everyone, for your great interest and participation.